Hello, Trend in Research viewers. Today, we dive into the fascinating world of robotic navigation with the paper titled Mobility VLA, Multimodal Instruction Navigation with Long Context VLMs and Topological Graphs. This groundbreaking research tackles the complex challenge of guiding robots using multimodal instructions, merging text and images, to accurately interpret and act in real-world scenarios. Prepare to explore how this innovative approach enhances robot navigation systems to understand and respond to human-like instructions more effectively. Let's get started! Navigating the complex landscape of robot navigation, we encounter the significant challenge of interpreting and acting upon ambiguous and colloquial multimodal user instructions. Traditional methods often falter when faced with the nuanced demands of real-world scenarios, where instructions are not just textual, but richly multimodal, incorporating both text and images. To address this, we introduce the Mobility VLA, a pioneering vision and language model tailored for navigation tasks that require discerning high-level goals. This model stands out by integrating a detailed frame-by-frame analysis of a demonstration tour with the user's multimodal instructions. Through this innovative approach, Mobility VLA excels in understanding and executing user commands with remarkable accuracy, setting a new standard in the field of robotic navigation. Let's delve into the core of our research, focusing on the Mobility VLA system. This innovative system is designed to process interleaved text and image prompts, enabling it to pinpoint relevant frames within a demonstration tour video. What sets the system apart is its ability to handle long context sequences, extending up to 1 million tokens. This capability is crucial, as it allows the system to grasp a deeper understanding of the context, leading to more accurate and effective navigation decisions. By integrating these advanced features, Mobility VLA significantly enhances the robot's ability to interpret and act upon complex multimodal instructions. In this segment, we delve into the innovative Mobility VLA architecture, a cornerstone of our research. As illustrated in the figure on display, this architecture leverages multimodal user instructions combined with a demonstration tour video to pinpoint navigation goals. This integration of long-context vision language models, or VLMs, significantly enhances robot navigation capabilities. Our focus on multimodal instruction navigation, or MIN, is pivotal. It not only boosts robot usability, but also enriches interaction with humans. By employing advanced VLMs, our system adeptly handles a range of instructions, be they multimodal, colloquial, or ambiguous. This capability is crucial for developing robots that can understand and act on diverse human commands in real-world scenarios. In addressing the limitations of traditional navigation systems, we recognize their reliance on specific coordinates or limited language instructions, which often fall short when faced with complex multimodal user inputs. This brings us to the motivation behind our research: to overcome these constraints by integrating vision language models, or VLMs, that are adept at understanding intricate multimodal instructions. The specific problem we tackle is the challenge of high-level goal finding, which involves interpreting both visual and textual user inputs. Traditional systems have struggled to accurately decode these inputs, leading to inefficiencies and errors in navigation tasks. Our approach aims to refine this process, ensuring more accurate and context-aware responses from robotic systems in dynamic environments. This sets the stage for a deeper exploration into how VLMs can enhance robotic navigation by leveraging their advanced reasoning capabilities. Enhancing the naturalness and intuitiveness of human-robot interactions is paramount for integrating robots seamlessly into our daily lives. Traditional methods, such as client-based retrieval and text-only approaches, often fall short in real-world scenarios where instructions are multimodal and laden with ambiguity. To address these challenges, we introduce the Mobility VLA, a visionary long-context multimodal vision language model specifically designed for navigation tasks. This innovative approach leverages a demonstration tour video combined with interleaved text and image prompts, enabling the robot to understand and execute complex, colloquial instructions that previous technologies could not handle effectively. This capability marks a significant advancement in making robots more helpful and ubiquitous in everyday environments. As we delve deeper into the capabilities of long-context multimodal vision language models, or VLMs, it's crucial to highlight two key innovations that significantly enhance the performance of these systems in complex environments. First, the use of long-context processing, capable of handling up to 1 million tokens, allows our models to maintain a robust understanding of extended interactions and narratives. This is particularly vital in scenarios where the robot must navigate and act based on lengthy and detailed instructions. Secondly, this extended context capability not only improves the robot's understanding of its environment, but also equips it to handle queries that are out of the ordinary or distribution. This means that even in unfamiliar situations, the robot can make informed and accurate decisions, enhancing its autonomy and effectiveness in real-world applications. These innovations mark a significant step forward in our quest to develop more intelligent and adaptable robotic systems. Let's delve into the core of our research, focusing on the Mobility VLA, a pioneering navigation policy that leverages long-context multimodal vision language action, VLA capabilities. This innovative approach is specifically designed to enhance robot navigation by adeptly interpreting complex, multimodal instructions that are often colloquial and ambiguous in nature. Addressing the challenges faced by current robotic navigation systems, we introduce the concept of multimodal instruction navigation with tours, or MINT. This framework is crafted to tackle the difficulties in understanding and executing user commands that combine both textual and visual cues. By integrating these elements, Mobility VLA not only comprehends, but also effectively acts upon such multifaceted instructions, paving the way for more intuitive and efficient human-robot interactions. Delving deeper into the Mobility VLA, we explore its hierarchical structure, which is pivotal for its operation. At its core, Mobility VLA integrates a high-level vision language model, VLM, with a low-level navigation policy. This combination allows the system to process complex, multimodal user instructions effectively. By utilizing a demonstration tour video, the VLM can pinpoint goal frames that align with the user's navigational requests, demonstrating a sophisticated understanding of both the environment and the task at hand. Focusing on the high-level policy powered by our vision language model, it's important to note the model's capability to handle long context sequences, which can be up to 1 million tokens. This extensive context length is crucial for deep environment understanding, allowing the VLM to make informed decisions even in complex scenarios. The model uses a specific prompt structure, denoted as P, F, N, D, I, which interleaves text and images. This structure guides the VLM in processing and responding to the user's multimodal instructions, ensuring accurate and relevant navigational outputs. By leveraging these advanced methodologies, Mobility VLA sets a new standard in robotic navigation, particularly in how robots interpret and act on human instructions in real-world settings. Diving deeper into the Mobility VLA, let's explore the intricacies of our low-level navigation policy. Once the high-level vision language model identifies the appropriate goal frame from the demonstration tour, the real challenge begins, translating this information into actionable steps for the robot. This is where our topological graph comes into play. Constructed meticulously from the tour video, this graph is not just a map, but a dynamic blueprint that guides the robot through precise waypoints, ensuring smooth navigation in real-time environments. Transitioning to our training and evaluation pipeline, the process begins with the integration of multimodal data. This is crucial, as it allows the Mobility VLA to process and understand both visual and textual inputs simultaneously, mimicking human-like comprehension. The demonstration tour video is broken down into frames, each annotated with multimodal user instructions. This rich dataset trains the VLA, not just to recognize objects or spaces, but to understand complex user intents and contextual nuances, setting a new standard in robot navigation systems. Delving into the technical core of our research, the Mobility VLA employs a sophisticated algorithm to interpret multimodal inputs effectively. This process begins with the VLM analyzing both text and images to extract meaningful context. By leveraging advanced computational techniques, the model integrates these insights to pinpoint the precise navigation goal, demonstrating a nuanced understanding of both visual and linguistic elements. In terms of experimental design, our approach was rigorously tested against several baseline methods. This comparative analysis not only validates the superior performance of Mobility VLA, but also underscores its practical applicability in real-world scenarios. Through these experiments, we've established a clear benchmark for future developments in multimodal understanding and navigation systems. Let's delve into the key results and improvements achieved by Mobility VLA. Our findings demonstrate that Mobility VLA significantly outperforms other methods in high-level goal-finding tasks. Specifically, it achieved an impressive 86% and 90% end-to-end success rates in complex navigation scenarios, which were previously infeasible with other technologies. To illustrate, consider a scenario where the user instruction was ambiguous. "I want more of this," accompanied by an image of Coke cans. Here, Mobility VLA excelled by correctly identifying the refrigerator as the target destination, showcasing its ability to interpret multimodal cues effectively. In contrast, other baseline methods struggled, either misidentifying the target or failing to provide a clear response. These examples underscore the practical effectiveness of Mobility VLA in understanding and executing complex, multimodal instructions in real-world environments. This capability marks a significant advancement in the field of autonomous navigation and interaction. Moving on to our technical results, let's delve into a qualitative analysis that highlights the effectiveness of the Mobility VLA. Consider a scenario where the user provides an image of Coke cans and instructs the system to find more. Here, Mobility VLA excels by correctly identifying the goal frame that leads to a refrigerator, showcasing its superior ability to interpret complex and ambiguous multimodal instructions. This contrasts sharply with other models that struggle to derive accurate interpretations from similar inputs. Additionally, our ablation studies shed light on the significant impact of long context processing capabilities. By enabling the model to process up to 1 million tokens, we observe a marked enhancement in both accuracy and the model's ability to comprehend intricate instructions. This capability is crucial for navigating the nuanced demands of real-world applications, ensuring that our system not only understands, but also accurately acts on complex multimodal prompts. The technical results from our study underscore the indispensable role of long-context multimodal vision language models, or VLMs, in navigating complex tasks. These findings are not just pivotal for understanding how these models process and execute navigation instructions, but they also open up exciting possibilities for their application beyond the tested scenarios. Firstly, the results confirm that long-context multimodal VLMs are crucial for interpreting nuanced and often ambiguous user instructions in real-world settings. This capability is essential for developing autonomous systems that can effectively operate in dynamic and unpredictable environments. Secondly, the implications extend to broader applications. The success of these models in high-level goal finding suggests potential uses in various robotic systems, enhancing their ability to interact with and adapt to human-centric environments. This could revolutionize how robots are integrated into everyday life, from personal assistance to industrial automation. In essence, the technical prowess demonstrated by these VLMs could be a game-changer in the field of robotics and artificial intelligence, paving the way for more intuitive and responsive systems. As we conclude our presentation, let's reflect on the significant strides made with the introduction of Mobility VLA. This innovative long-context multimodal vision language model has set a new benchmark in navigation tasks. By effectively processing complex, multimodal instructions, Mobility VLA has demonstrated a remarkable ability to identify high-level goals, outperforming existing methods significantly. The figure displayed here offers a qualitative comparison, showcasing the intermediate outputs of Mobility VLA against other approaches. This visual representation clearly highlights how our model excels in understanding and responding to nuanced user commands, a testament to the practical applications of VLMs in enhancing robotic navigation systems. These contributions not only advance the field of autonomous navigation, but also open up new avenues for research in multimodal machine learning. Thank you for your attention. As we conclude our exploration of long-context multimodal vision language models, let's reflect on the key takeaways and their implications for future research. First and foremost, our findings underscore the critical role of long-context multimodal VLMs in accurately interpreting and executing complex, dynamic instructions. The success of the Mobility VLA in high-level goal-finding tasks demonstrates the potential of these models to significantly enhance robotic navigation and interaction in real-world environments. Looking ahead, this success invites further exploration and development of long-context VLMs across various applications. Whether in service robots, assistive technologies, or industrial automation, the principles we've uncovered have broad applicability. Finally, our results suggest potential improvements in VLM training methodologies. Enhancing the understanding and interaction capabilities of these models in human-robot interfaces could lead to more intuitive and effective communication, paving the way for robots that better understand and respond to human needs and contexts. These insights not only propel the field forward, but also open up exciting possibilities for future innovations.